Okay, so let's continue then. So now we have talked about Ethernet and showed a little bit about how a practical protocol can look like. Now that's a local area network protocol, Ethernet is. So sometimes we would like to collect smaller LANs and make a bigger LAN out of it. So how do we connect different LANs with each other? So then there are three main ways we can do that. We can use repeaters or hubs, and these are layer 1 devices, basically that process only the physical layer channel, does not look at any addresses or anything like this. Or we can use something called bridges or LAN switches, and these are things that work on the link or MAC layer. So this is layer 2 devices, these are layer 1 devices. And then we can have routers, and these works on the network layer, and these are layer 3 devices. Okay. So when connecting networks, we can do that in many different ways, either on the physical layer, the link layer, or the network layer, right? There is no need to connect them on higher layers than that. Okay. So if we look at, for instance, the ordinary TCP/IP stack, we have IP, which is the network layer that connects everything. And then below that, there is these link layers that could be Ethernet, Wi-Fi, whatever. And then on the lower layers, we have lower than that, we have bridges, hubs, and so forth. So what can we say about these? Repeaters, or these hubs, are very simple devices, but does not scale to large networks because all traffic is then broadcasted in all connected networks. So if I have two LANs like this, I connect them together with a hub, it becomes a big LAN. So all the hosts are competing for one medium, right? However, if I have a switch like this, essentially this cable is one LAN, and it is independent of this LAN, which is independent of this LAN. So we connect here, the input ports here, we can think of this as connections to LANs, which are logically connected to each other, but not electrically, right? So they form a bigger network, but competition for the cable is only constrained to those hosts which are connected to that cable or that LAN. Right? So it scales better, but it's also a little bit more complicated device. Now, if this would happen to be a router instead, it would be a more complicated device, but with a higher performance in the sense that it scales better with the number of attached networks. So, when reading about switches in the literature and on Ethernet, on the internet, you would see switches sometimes called layer 2 switches or layer 3 switches. Okay, so there are also switches which are layer 3 devices. However, for the simplicity of this course, when I say a switch, I mean a layer 2 device. I won't talk about layer 3 switches except in few cases, and then I will make sure to make a point that I talk about that then. Okay. So traditionally, hubs, physical layer devices, layer 1 devices, switches, layer 2 devices, routers, layer 3 devices. All of them connect networks together, right? Pros and cons with all of them. If we want to look this in a protocol, let's take a practical protocol stack, the ones which are by 802, so IEEE one. So suppose we have some network here, and they're a network layer here. Then it goes down to an LSE layer, and then say that this is a Ethernet layer. Okay, so IEEE Ethernet, and then it's using the physical layer 10 base T. So this is a 10 megabit Ethernet with these type of twisted pair cables. And then it goes over these twisted pair cables into a link layer bridge. Okay, bridge is the same as switch. it's the same thing, right? Now, then it goes up here in the physical layer, it goes up to this MAC layer, it goes up to the link layer. Now, suppose that the address as such is that it needs to go over to some device here, which is connected with the bridge here using 802.11, so Wi-Fi, that uses 802.11a physical layer. Then this is actually a radio channel. It goes over the radio channel and goes up like this. Okay, so essentially now this switch is not such a switch, but this switch only goes from Ethernet to Ethernet, but different types of Ethernet would be okay. It could be a 10 megabit Ethernet here, it could be 100 megabit Ethernet here. Yeah, there's no gigabit Ethernet in this one, but that could also be the case. But it could be also a little bit more complicated device with an antenna on top of it. Then it would be Ethernet, 10 or 100 megabits perhaps, and then Wi-Fi here. So this is also known as an access point. We'll talk more about that later on. Okay, so in a device like this, a link layer bridge, the most complicated version of those can handle multiple network layers. I don't know why it says network layers here. I think the main point here is that we can handle different types of MAC layers below the link layer in this bridge. So let's do it like this. Okay. However, then if we do that, then the frame format on this LAN is quite different from the frame format of this, which means that whatever frame we get up here needs to be reconfigured when we go down here. All right. So it's different frame format here and here because it's different. Well, first of all, it's different signals because it's different physical layers, but there are also different frames because of the frame formats of these MAC layers are different. Okay. Yeah. To simplify things, if we have the same MAC layer here, there is no need for doing frame translation, because the frame that goes up here is the same frame format that goes down here. Could be still different physical layers. For instance, as I said here, it could be 100 megabit physical layer or 10 megabit physical layer, but it's still Ethernet frames, right? Same MAC layer, and therefore it's a simpler device. So there is no need to translate between frame formats. Now, when plugging this in, we would like it to be plug and play. Okay, in the sense that whatever we plug in here should just work. That's the idea. And it will just work if this is a transparent bridge. Okay, so what do we mean by that? It means that if we have a topology that looks like this, we have one LAN here. Suppose this is an old-fashioned Ethernet with a coaxial cable, just to simplify things. And we have another LAN like this. And we would like, for instance, this host to be able to communicate with this host. Then we need to connect these, right? And then we use a bridge between these two LANs. Now, ideally, from a maintenance point of view or deployment point of view, when we plug in this bridge, we don't want to reconfigure the hosts for this, and we ideally don't want to configure this bridge at all. We just want to plug it in. And so we will see how to do that later on, how we can do this actually. Nevertheless, how we do this, the precede logical topology would look something like this. So the host which is down here and the host which is up here seems to think that they are connected to the same physical LAN, even though they are not, because they have a bridge in between. But this bridge is invisible from the perspective of the hosts. Okay. So what we would like to do is to connect LAN transparently. Okay, what does that mean? It means that the stations should not notice the existence of this bridge. So these hosts here have no clue that the bridge is here. It doesn't interact with the bridge in any particular way. That doesn't communicate with this at all. In the sense that, yeah, let me show how this works later on. So this works if the bridge then learns what to do by inspecting addresses of the frames of the LANs attached to it. So if there is like this, where a frame needs to go from this host to that host, the frame goes out on the LAN here, right? And it goes to all the attached nodes, including the bridge. The bridge looks at the destination address, okay, and figures out, okay, it needs to go all the way here. And then it also goes this, but that's useless, right? It needs to anyways go to the right here. While say that this host here would like to talk to this host, they are on the same LAN. So when the host transmits out its frame, it goes to the destination right away. It also goes to the bridge. It also goes to that host on here. Now the bridge inspects the destination address and figures out, okay, it should not go to LAN 1 because the end destination is on LAN 2. So it blocks it. Okay. So how does this functionality, how is this implemented? We use something called backwards learning. And I think the easiest way to figure this one out is to look at an example. So look at this topology here. Consider this topology. We have 3 LANs. We have LAN 1, LAN 2, and LAN 3. 2 bridges, B1 and B2, which are connected to this. Bridge 1 has 2 ports, port 1 and port 2, and bridge 2 also port 1, port 2. In the beginning, when we power this up, they have routing tables or forwarding tables or switching tables. Actually, it should be called a forwarding table that are completely empty. And what we want to do then is to put in the MAC addresses here. Okay, so what we would like to do is populate these such that we have a MAC address corresponding to a port where that MAC address is heard. Okay, so let me show how this is done. So suppose that there is a frame that is sent from S1 to S5. So we transmit from S1 to S5. That's what we want to do. In the beginning, we powered up this network. The bridges knows nothing. Right. So the first thing that happens is that the frame is then put out on the medium. There is some competition for the medium through the MAC protocol, but anyways, eventually it's transmitted. And then it's transmitted and picked up by all nodes on this network. But since S2, which is connected to this network, is not the destination, it will ignore this packet. However, the bridge picks this up. Okay? And what has the bridge learned? Well, it has learned that there is a node called S1 on its port number 1. Okay? So it knows that S1 is on port 1. Right? This is what the bridge knows at the moment. However, it doesn't know where S5 is because S5 is not in the table here. So the bridge then play it safe and say, okay, maybe S5 is here to the left, maybe S5 is to the right. I don't know. Okay, but let's play it safe. I just put it out on my other port here because maybe S5 is here. I don't know. But anyways, it sends it over to the other LAN, LAN number 2. S3, of course, ignores this frame because it's not destined to it. It's not the destination. But then bridge number 2 picks this up frame and then inspects it and see that, okay, apparently there is somebody called S1, which is on my port 1. So I put this into the table. Do I know where S5 is? No, I have no idea. But, you know, I send it out on port number 2 just to be safe. Maybe S5 is here. I don't know. But to play it safe, let's put it out here also. Which happens to be the right decision in this case. And now S1 has reached S5. So connectivity has happened. which is good. And we also have learned something. Both these bridges now know a little bit about S1. It knows that from bridge 1's perspective, it's attached to port number 1. For bridge 2 perspective, it's also attached to port number 1. It's port number 1. Any questions so far? Okay, so let's continue to learn. And we learn by inspecting, if we are the bridges, we learn by inspecting the traffic which is ongoing on our ports. So if S3 now decides to send something to S2, what's going to happen? S3 generates a packet from S3 to S2. This is picked up by the bridges. Okay. So what do the bridges do now? Well, first of all, bridge 1 sees that, okay, S3 is apparently on my port 2. B2 sees, okay, apparently S3 is on my port 1 and fills out the table. Okay, next thing to do is to look at the destination address. So bridge number 1, what does it know about S2? Nothing, right? So it has to put it out on port number 1, all its ports actually. Now it's only 2 ports here, but they put it out on all the other ports, except the port that they just got it from, right? Same thing goes with bridge number 2. And then these packets are then sent out on LAN 1 and LAN 3. Now, it was completely useless at LAN 3, but the bridges didn't know this, right? So it's harmful in the sense that it takes up some space here, but at least it goes to the right destination. So we ensure connectivity and we learn something. Okay. Questions? No. So let's continue. So soon it will become a little bit more interesting here. So from S4 to S3, what happens? Well, a packet is generated at S4, has the right destination address. It goes to bridge 2. Bridge 2 learns that apparently S4 is on its port 2. And then it looks at the destination address, S3, and it finds it in its table. Okay, so it knows that S3, whenever there is a packet to S3 coming to this bridge, it should go out on port number 1. Okay, so it forwards the packet to port number 1. It goes over the out port number 1 and is picked up by S3, and it's picked up by bridge number 2. So now connectivity has been established from S4 to S3. So what does bridge number 2 do? Bridge number 1 do? Well, it looks at the source address and puts that into the table here. Okay, and it looks at the destination address, S3. It knows that S3 is on its port 2. So what to do then? What should it do? What should the bridge do now? Yeah, nothing, essentially, right? Because the bridge knows, okay, here was a packet that came in. It's headed to S3, but I know that S3 is on my port here already. It's on the same port that I received it to. So I don't do anything. I just drop the packet, right? There is no need to forward that because that is useless. I know that S3 is to my right here. Okay. Okay, and then we continue like S2 to S1. What's going to happen then? Well, S2 generates a packet, transmits this out. It's picked up by the bridge and the destination. The bridge knows that what it does is, okay, so apparently S2 is on my port 1. So I put that into the table like this. I also know that S1 S1, I know that that is on port 1, so I do nothing. I learned something, but I do nothing with the packet as such. Right. So any questions on this learning strategy? Okay. And notice now that there is no configuration by a human here. Right? We just plug in the switch, and the switch will just monitor what's going on onto its port, build out a routing table in front of it, and when this routing table is stable, it can filter efficiently. If it doesn't know anything, it acts like a hub. Right? Whatever comes in goes out, and it goes out in all the ports because it knows nothing, right? So that's the safe thing to do. So it starts like a hub and ends like a filtering switch. Questions? Okay. In a static network, so what is a static network? Well, there is somebody has plugged this in, and then we wait for a few minutes, and then things are stabilized. Then, if nothing else changes, eventually the routing table here will be populated, and everything is cool. Nothing changes. Now, if there is a change, or if one node which is attached to this one moves to some other place, then there is a change in topology, and we need to relearn things, right? So in practice, there are timers associated with each of the entries in the table. There's a timer also. So if I haven't heard anything for some time, then I scratch out that part of the routing table. Or if I hear that station number 1, which I heard on this port, if it somehow ends out in this port, and I hear station number 1 on the new port, I update the routing table accordingly, right? So I just use the latest information I have, and when the information gets too old, I forget about it, right? So that's the way to handle dynamic networks. Now, so there is a problem with this. And the problem is when we have topologies where we have loops in them, because then this learning strategy will fail. Okay, the routing tables will be messed up, or forwarding tables will be mashed up. So to show how to resolve this, and also potentially show a little bit of the problems that can occur here, is that suppose we have a network like this where we have 4 LANs. We have LAN 1, LAN 2, LAN 3, and LAN 4. And we have a bunch of bridges which are connecting these 2 LANs here. And in particular, let's look at LAN 1 and LAN 2. And we see they're connected with 2 different bridges, bridge 1 and bridge 2. This is unnecessary, right? I mean, it's enough with 1 bridge in this case. Why would we ever have 2 bridges here? Redundancy, correct, yeah. So it's good if one of these fails that there is a backup, right? So that's one reason. The other reason, what could that be? It's a little bit of a trick question. Yeah, that could be a little bit. But the more likely thing is that somebody messed up, right? Somebody connected the wrong networks together, right? Happens all the time, right? And instead of breaking the network, we would like the network to somehow realize this and correct for this. And the problem is when we get a loop like this is that, I mean, how should we form the tables here? We can have a packet actually flowing around in a circle like this, never-ending circle, and causing updates to the routing tables all the time. And eventually the whole network will break down because there is all these networks flowing around here, never dying, never ending, just updating the routing tables here. So one can easily construct an example of this. So I won't spend time on this now because we're a little bit short of time. But if you look at the book or look online, if you look at this known sometimes as a broadcast storm, you can see that this is actually a problem in practice. So what we want to do then is that, okay, we want this redundancy, and we want the network also to be resilient towards manual mistake. Right? So somehow we would like to convert this physical topology into a logical topology where we have removed the loops. Okay, so that's the idea now. Okay, so just to reinforce, loops can cause severe problems for the learning algorithm. To remove the loops, we can logically disable links, bridge ports, such that the resulting topology is what's called a spanning tree. Spanning, that means that all nodes are connected, and tree means that the topology has no loops. So a tree structure looks something like this, and you see there are no loops here between different things. Okay, so let's see how this works. There is a spanning tree algorithm, and we'll go through an example. I'll just put this down in text first. So what we want to do is we would like to select a bridge among all bridges to be the root of the tree. Okay, so that needs to be identified. And how to choose the root bridge, we can do that in different ways. Let's have the simplest thing we can think of, is that suppose each bridge has an ID. Out of all the connected bridges, we pick the bridge with the lowest ID and say, okay, you're the root. In practice, this is a little bit more refined way to do that. But let's just assume that each of the bridges have a number that's unique in the sense that there is one which is the best. Okay, lowest. Okay. And then for each bridge, except the one which has been elected as the root bridge, we determine the root port. Okay, and what is the root port? Well, here we have 5 ports. Okay, and one of these ports is the best port in the sense that it has the closest path or best path to the root, wherever the root bridge is. Okay, so the root port is the port with the least cost path to the root bridge. And then for each LAN, we select a designated bridge and its designated port. Okay, so what is this? A designated bridge is the bridge which is connected to the LAN, which has the least cost path from the LAN to the root bridge. Again, this will be a little bit clearer than when we look at the example, but this is the definition of the designated bridge. The designated port is the port that connects the LAN to the designated bridge. Okay. All root ports and all designated ports are placed in a state called forwarding state. That means that these ports are allowed to receive and forward frames. All other ports are placed in a blocking state, which means that they are not used. Okay. To forward frames. Okay, so let's see how this works. We power up, we know nothing, right? We know, since we see this, that there is a loops in this. So how can we resolve this? The first thing to do is we have bridge 1, 2, 3, 4, and 5, and we need to select the root bridge. Which one is the root bridge here? The one with the lowest ID, which is bridge, the conveniently numbered 1 to 5, so it's bridge number 1, right? Okay, so the first thing we do is to it was messed up here. Okay, so the numbers after B here is the bridge ID, and these numbers with parentheses around is the port IDs. So the first thing we do is to select the root bridge, which has the lowest ID. Okay, and here we go. So this is the root bridge. That's step number 1. Then step number 2 is to select the root port for each bridge. Okay, so what is the root port? It is the best port to reach the bridge, and it's best port in terms of having the lowest cost. And here we assume that once we need to go over a LAN, it costs 1. Right? If I need to go over 2 lawns, it costs 2. So each lawn that we traverse has an additional cost of a unit, 1. Okay, so what are the root ports here now? So for bridge number 2, we have 2 ports, 1 and 2. So if I want to go to the bridge, okay, so I want to go to the route from bridge number 2, which port should I choose? Well, I have 2 choices, 1 or 2. If I go over 1, I need to go over 1 lawn, so that's cost 1. If I go over lawn 2, I also have cost 1. So I have 2 ports which are equally good. But I have to select one. So then I select the one with the lowest number. Okay, 1 is less than 2. So now I know I have the root port like this. Fine. So what is the root port for 3? Well, for bridge number 3, we have 3 ports, 1, 2, 3. And see, here it costs 1 to get to the root. For port number 3, I need to go over 1 lawn, 2 lawns, 3 lawns to get to the root. So that's a worse port. I can also go like this, 1, 2, 3, still worse. Port number 2, 1, 2, or 1, 2, 3. Not a good one. Okay, so here the best port is number 1. So that's now the root port for bridge number 3. And we continue to do this for the other ones. So B4 has port number 1 as the root, and B5 also root. Okay, fine. So now we know the root and we know the root ports of all the bridges. Then the next step is to select a designated bridge port for each lawn. Okay. Now for the root, it has, okay, from the perspective of lawn 1, which is the best port to get to the root? Well, it has to be number 1, because then I'm at the port, I'm at the root. Okay, so then this becomes then the designated port for lawn number 1. For lawn number 2, okay. Okay, so I don't know if I missed the animation here. For lawn number 2, it has 3 ports to choose from. Which one is the best? Well, it's this one, because it's closest to the root. So this becomes then the designated port for lawn 2. For lawn 3, it has this port, and this port to choose from. And this one has, what is the cost to go to the bridge from here? Well, it has to go over 1 lawn. Here it also has to go over 1 lawn. So it's equally expensive to go up here as going up here. Nevertheless, we choose this one because 3 is less than 4. So we have a tiebreaker here in the bridge ID. So then this becomes the designated port. And then for the, for lawn 4, we have this choice or this choice, and then this happens to be the best choice. So now we are ready. We're done, actually. We have, first of all, we have selected the route. We have selected the route ports for each other bridge. And then for each lawn, for lawn number 2, we have selected the designated port and therefore also the designated bridge for lawn 2. For lawn 1, this is the designated port and this is the designated bridge. For lawn 3, this is the designated port and this is the designated bridge. And for lawn 4, this is the designated port and B3 is the designated bridge. And all ports which are not routes or designated are disabled. And then we have a loop-free topology here. Now, these ports are logically turned off, but could be turned on a little bit later if there is a network failure somewhere. Questions on this?
Is this done automatically?
This is done automatically. So there is a protocol for doing this. So there is no manual configuration of this, just as adaptive learning or backwards learning is automatic. I mean, in the sense that there is no manual configuration. Okay, so then if we then have a host which is attached to LAN 4 here, so we have a host, and it would like to talk with a host which let's call this host A, and then we have a host B on this one. Now, if there is some data that needs to go from this host to that host, what is the physical path it will take? Well, it will go over the LAN. It will be picked up by all the hosts which are on the LAN, but more importantly, it will be picked up by this bridge, right? Because this is the designated bridge for that LAN. And it will inspect its routing table and figure out, okay, it needs to go up here to the root, and the root would then forward that down here, like this. Okay. So if the hosts are attached to LANs which are on opposite sides of the root, all the traffic goes up the tree until it reaches the root and down to the appropriate leaf. Right. Of course, if data needs to go to a host which is on the same LAN, then data just goes this way, right? It goes never by the root. But you can maybe imagine that there could be cases where the root has a lot of things to do, right? Forwarding traffic back and forth, back and forth, back and forth, right? So maybe this is not a super efficient solution to this. So there are modern ways, other ways to do this, where instead of using spanning trees, we allow for also these disabled ports to be connected, and then when data is flowed in another way. But that's outside the topic of this course. But I just want to make you aware of that the spanning trees were an early technology that was put in place at the beginning. But afterwards, when we have very big LANs with many hosts, this scales pretty badly due to the fact that we have a root here that could be overloaded. Okay. Right. So just a few words on the actual protocol that does this. So there is we did this, we created this by just inspecting the network. But of course, the network bridges doesn't have an idea what the network is. It's completely blind to this. So it doesn't have this helicopter view. So this was indeed a problem. And then the story is that Raida Perlman, who was then hired as an engineer, was given 1 week to fix this problem. Right? And in 1 week, she figured out what to do. Really a smart lady, I would say. So she has a PhD in mathematics from MIT, which is a very nice school. So she figured out what to do, basically, how to create these spanning trees. We don't have time to go through the protocol here, but it's quite ingenious. And the idea is that one has a distributed algorithm to elect the root. And once you have done that, you also have learned what the cost to reach the root is, and then you can assign the designated ports for the bridges, and then we're done. Right? Yeah, so I won't go through this in any detail. So I think we will just simply finish here. And then on Monday, we will continue our journey. I think it's maybe time for Wi-Fi, if I remember correctly, on Monday. Otherwise, it will be something else. So, see you then.
Men jag ska köpa tillsammans med
Vad sa du? Ja.